I would like to welcome you all in the first technical scientific session of this Indo-US webinar and lecture series. And we are going to start this session with the plenary lecture by Professor D.D. Sharma on a very hot topic, miraculous world of materials.
So I'm going to talk about the miraculous world of materials. Obviously, as I told you, materials have been miraculous and shaping the world from time immemorial. So there is not going to be any way I can cover the spectacular properties that have defined mankind in its progress. But I'll take every example from modern times to tell you how wonderful, how counterintuitive, how exciting properties can be seen in different kind of materials, leading up to a particular material that I'll talk about a little more, which is of very recent vintage and something that you're interested in. But I'll not be talking about the why of it, but I'll show you what of these materials. That is the purpose of this talk. For example, if I start talking about polymer materials, all of you have heard of polymer materials, and they're a nuisance in terms of plastic bags, for example, creating havoc to the ecology, environment. It's a terrible thing, but also it has many extraordinary properties. The reason that they are a menace today is because they're being used so extensively. They're extremely useful also. The particular polymer that I'm going to show you examples of and tell you why it is so exciting is this super absorbent polymer. And so there, what happens is, think of this. Okay, let me show you. Okay, I have to get back my pointer, I guess. Otherwise, I cannot start possibly. Okay, yes. This video. So in this video, what I'm going to show you is, this is also known as diaper polymer for obvious reasons. This is the polymer that you can see here, and I'm pouring water into it. And you saw there was very little polymer and a full of water that I've poured, and you see what has happened. The entire amount of water that was poured into that polymer got absorbed by the polymer and sort of solidified and held inside. And you could see the volume of water that it can absorb is 10, 20, 30 times more than the volume of the actual polymer. This is the kind of absolutely miraculously that it absorbs and holds in water. And this kind of polymeric things, normally they are known to be highly insulating. But we can make many electronic materials out of it. We can make them conducting, we can make them semiconducting, we can make them insulating. And because they're polymer, they can be bent. And in fact, there's a lot of applications that are coming up in the near future where we'll be using polymer for various kinds of, let me try to see if is this part coming on the screen, covering part of the top of the screen? I don't know how to get rid of that. Okay. Anyway, let me continue and maybe. Okay. Yeah. So the polymer can be bent so that these are making what we call the wearable electronics. So in the future, we're thinking of human beings wearing polymeric electronics on their body, which will harvest the body temperature to power themselves. So this will be automatically powered. You don't have to generate power separately for them. The display can be bent, and as you can see, Samsung here, with actually, they have prototype materials. There's a mobile that can be flexed, bent. You can have roll them up and carry them in your pocket and do what you want, which is really unthinkable because we have been taught to think of electronics in terms of silicon architecture, which is extremely brittle and inflexible. But today we have the possibility of flexing the electronics because we have been able to make polymers, conducting, semiconducting, and of course, insulating. There is some difficulties I'm facing. Okay. This is shape memory alloy, another video. You saw that spring. The spring is now being distorted heavily, totally out of shape, as you can see. rotating, twisting, doing all kind of very, very nasty things. And once I have completely bent it out of shape, as you can see here, what we're going to do is to gently heat it up, as you'll see in a moment now. And once we start to heat it, the reason we call it shape memory alloy, as over here, you'll understand it right away, that as we start to heat, see what happens magically. The spring remembers the shape that it started off with and goes back exactly to that shape, such that as if no distortion was given. That means this is an alloy which memorizes its shape. Even if you distort it drastically, it can get back to that shape if you give it slight amount of energy. What is the use of this kind of material? This kind of material has actually totally changed our life in a spectacular ways, in many different ways. I'll give you only a few examples. You see these tube-like things that are here made of this shape memory alloy. These are the stents. You may have heard about stents being put inside the arteries and veins of human body when they get clogged up. The way it is done is that you want to put something inside these arteries and then open it up such that the arteries remain open. But in order to get it inside the artery, it cannot go into the open state. What you have to do is to collapse into a very compressed state. For example, this object that you can see here, let me pick up the laser pointer once again, that this object here is very small. This is the object, when given the right kind of excitation, will become as big as this one. So you make it contracted like this, push it into the arteries, and then warm it up slightly so that it can expand and become a stent of the right size that you want. These shape memory alloys are also used extensively for dentistry, in robotic arms, in surgeries, even in making glass frames, spectacle frames. So they're being extensively used due to this very surprising property that you can bend them, twist them, and do what you want. But then they can come back to the original shape because they remember that original shape. And shape memory alloys have really revolutionized our life. Some other miraculous materials. This material over here is a powder. It's an oxide powder V2O3. And such black powder, if you remember in school, you were taught that something is metal and something is insulator, and the difference between a metal and an insulator was defined that metal is shiny, insulator is not shiny, metal is malleable and ductile, insulator is brittle and not ductile. So from all that characteristic, this powder here looks like an ideal insulator. This powder has this fantastic property. And what I'm showing you is resistance as a function of temperature. Because also you know a metal is something that has low resistance and insulator has high resistance. That is the most fundamental property that comes to mind when you talk about metal or insulator. This material at low temperature, let's say about 100 Kelvin, has a resistance that is about 10 to the power 8 ohms, that is 1000 mega ohm resistance for some particular shape and size of the sound. And the same material, if I heat up to 180 Kelvin, becomes such a low resistance. So you see that the resistance is changing by a million-fold, going from 10 to the power 2 to 10 to the power 8 just by changing the temperature. It is like taking an insulator and converting it into a metal with a huge change in its properties. And that's why this has been often called as that this part, it's copper-like, it conducts as well as copper. At this end, it is as insulating as glass. And it is the same material that just by changing slightly the temperature can go from a metal to a glass-like. And that can, of course, be put to many uses, but it's also spectacular. And many decades we are spending. Even today, we are trying to understand its property, why it happens the way it happens. And it has remained one of the favorite question of scientists. They keep going back to every decades trying to understand this spectacular property. And so I thought that I should familiarize you with this particular kind of examples. Of course, not only metal to insulating. You can have a metal. Again, I'm showing you resistance here and temperature here. Typically, as I lower the temperature, metal's resistance decreases gently. But then there are some metals which, when you reduce the temperature, suddenly at one particular temperature, its resistance goes all the way to zero. And this state where its resistance has gone to zero, we call it the superconductor. So metal can become a superconductor. There are also examples where an insulator, starting as an insulator at one temperature, would become a superconductor at a low enough temperature. Such, it is like, this is the typical road condition where if you are trying to drive a car, you're getting scattered and stopped by other cars, you cannot move fast. And that is the situation with normal metal. At high temperatures, it's like having more traffic here, more scattering, getting stuck with other vehicles. But as you go to below this transition temperature, what you call the TC, the transition temperature, suddenly there is no obstacle in your path and you can move as freely as you want, becoming in this superconductor. This Meissner effect, let me see if it doesn't start. So I have to again change over to the, let me see if I can, this is, okay, so what I'm showing, this is a superconductor at a certain temperature, looks like an insulator, and this is a magnet. Now I'm cooling it down with putting liquid nitrogen, and you see that magnet levitates on top. And it's freely floating in the air because there's a superconductor there, you can see, and it can be, and there's liquid nitrogen. As long as liquid nitrogen is there, it will be behaving that way. Now I can pull up that superconductor, put it here, now it will start to warm up and it will become a metal. And as it becomes a metal, you can see that the material drops down, magnet drops down on top of it. So that means that I can levitate a magnet on top of a superconductor when it is a superconducting state. And if I take it out of the superconducting state, it will come down and rest on top of it. And this particular thing can be used actually to make a magnetically levitating any object. For example, if in a train. This example is not on a superconductor though. It is using magnets only to float this train, but there can be also this magnetically levitated trains can be made with the use of superconductors. And then you can imagine that this will have no friction and it will be driven very fast and automatically, and it can be driven not only fast but using very little energy, because all that you have to overcome is the air friction, resistance of air, but the friction coming from the track, which otherwise dissipates a lot of energy, because much of the fuel or the energy consumption to drive any vehicle of this kind would be reduced drastically. That's very exotic material. So we don't have to think of only exotic materials. Even, as I said right in the beginning, any material that you can think of has some interesting properties. For example, if you think of soot, the soot that you find coming out of a diya, if you light a diya, or from the chimneys, the black soot that comes out, that contains various forms of carbon. Carbon itself can come in many different forms. And what I'm writing for here is 3D, tells us it's a three-dimensional form of carbon. This is two-dimensional form of carbon made from this one. This one is actually nothing but many, many layers of carbon, graphene put on top of each other. Each of these dots you are seeing is actually a carbon atom. And the stick that you're seeing is a bond between carbon atom, making this hexagonal pattern. And this hexagonal pattern makes a beautiful two-dimensional sheet. If you put many of these two-dimensional sheets one on top of the other, you get the well-known graphite. And that graphite can peel off, make it a graphene. And that graphene you can roll up and stitch it together by many techniques to get what is known as nanotubes. These nanotubes can come in various forms depending on how you roll, how many you roll, so on and so forth. And also this kind of structure, only with carbon atoms, you can stitch them together to form a ball. a buckyball, a football-looking object, and there are many different ways of, again, making closed object of that kind, and that's called the fullerene. The class is called fullerene. So this is a three-dimensional object, this is a two-dimensional object, as you can see. This is a one-dimensional object because it's closed on these two directions, but in one direction it's long, and this is closed on all three directions, so it's a zero-dimensional object. And these objects, just all made from carbon, have spectacular properties, as I'll be showing. This is the different ways that nanotube can be formed. Let's not worry about that. Carbon, you can take this nanotube and couple them together. Many of these nanotubes make a cable by joining them together. And for cross section, let's say 1 square millimeter. Millimeter is very small. It's 1 square millimeter cross section. You make a wire out of it. That wire, that cable, can hang 6.4 ton weight from it. It is the toughest material, the strongest material that we know of. In fact, it is so strong that one thinks of Arthur C. Clarke, the very famous science fiction writer, had visualized one of the best way of exploring space is to make space stations which can go up and down. And using these tremendously strong cables running up to some space station, and supplies can be sent by using the space elevator going up and down. That was a fiction when he wrote. He didn't know about carbon nanotube. But carbon nanotube has the ability to carry so much of weight that you can actually, and it has so lightweight that it can make such applications feasible one day in the future. In fact, the best known material that we have been using, high carbon steel, its specific strength is something like 154 kilonewton meter per kilogram. Whereas I don't know if you can see the number up here. From nanotube, the specific strength you can achieve is 48,000 compared to 154. Right? Now you can see 48,000 kilonewton meter per kilogram. Sorry? Okay, so it is the best known specific strength material that exists today. And it is already being used extensively, the various carbon materials. Graphene, for example, and nanotubes also can make the aircrafts become lighter, and it's already being used. It's being used in flexible electronic materials because it has very interesting electronic properties. Since it's such a strong and tough material, it's being used in all kinds of tennis rackets, in making lightweight bicycles. All professional bicycles have extensive amount of graphite or graphene generated materials in it. And you can also make, it is very useful in making super thin solar panels because it can be also made to absorb light very effectively. You can also make the lightest material because carbon is one of the lightest, one of the lowest Z atomic number material. You see, it's an aerogel made with graphene, which is being supported on this thin fibers of this particular object that you see if you go walking, a grass flower. Of that, these fibers that are coming up, they don't even bend when it supports such a large object, simply because it's so extremely light. And yet, it is mechanically stable. So you can make lightest material with highest strength, and that has the number of applications that are possible are really enormous. Then, changing topic and talk about mobility. Another aspect that I want to show you about these carbon materials. Mobility is basically talks about electron transport. What do I mean by that? Think that I have racetrack like this, different racetracks, and I'm going to put different materials, and I want to take electrons from here to there. Because everything that we do, all electronic materials require electron to be transported from one place to the other. Why should the electron go from one side to the other? Because I apply a potential difference. When an electron finds, imagine this is about 1 centimeter, and I apply a potential. I have a battery, and I'm going to apply 1 volt across it, such that an electron released from here will try to go to that side because its energy will get to it. The question that I'm asking after 1 second, how far the electron will go. Remember, this is 1 centimeter, I'm applying 1 volt. It depends on the material I use. And now you see that if I want fast electronics, I would like to have highly mobile materials. In fact, highly mobile or electrons which can move faster are required not only for fast electronics, but for many applications, because I need to move the electrons very quickly. Otherwise, bad things can happen to the electron. Accidents can happen to the electron. So even if I have solar cells, the reason you need solar cell, the silicon highly pure, is to make the electron ability to move far quickly, such that I can get these electrons that are generated inside the silicon outside for driving the light that I have at home. So let me ask that question and say after 1 second, how far the electron? As I said, it depends. Some electron on this track, depending on the material, will go this far. And if I have very good material, it will go this far. How much is this far? And what are the materials? For example, silver. It's one of the very good metal. So it must be very mobile electron. In 1 second, if I apply 1 volt potential, it can go 56 centimeters. Silicon that I talked about, with which our solar cell are germinated, can go 1400 centimeters, much more. Indium antimony, it is one of the best materials with highest mobility. It can go have electrons go 77,000 centimeters in 1 second, only with 1 volt applied. Carbon nanotubes can go 1 kilometer, 100,000 centimeters, 1 kilometer in 1 second. And graphene the electrons can go 2 kilometers in 1 second. Again, you can see that carbon that you have known from day one. In fact, graphene is what you use even before when you are learning to write. Your pencils are made from graphite material. And the trace that comes on your paper often, if you are using a graphite pencil, is this graphenes that are coming onto your surface. And that has this spectacular property that we didn't know about till it was discovered by undergrad, and they of course got to the present. Such materials are going to transform the world in many ways. In fact, nanomaterials in particular, I've talked about these nanomaterials, the ones that are made from graphene. Let me give you some examples of other kind of nanomaterials. In fact, nature uses nanomaterial. This is nothing but a lotus leaf, and many of you might have heard about the lotus leaf effect. If you see droplets of water on lotus leaf, it doesn't seem to stick. You can see it rolls off, and the ability to roll off is already shown by the fact that it's looking like a round drop. The reason it's a round drop is at the point of contact, it does not like to wet the material. For example, if you put a water droplet on paper, you'll find that it spreads because it likes to stick to the water and make the contact area as much as possible. Here, it seems it doesn't like to make contact, so it minimizes the contact and making the water as round as possible. We can make, and these actually keep the lotus leaf clean, because when they roll off, they collect all the dirt that is sticking on the lotus leaf like this and go off, and the lotus leaf remains clean. We can make, the reason the lotus leaf is this way is because it has these nanostructures that are shown over here, and you can make such nanostructures artificially, and here you can see one such surface that has been created, and you can see the water droplet on top of it, even more round than here. You can see that the water does not like to make contact, has minimized the contact with the material because I have made this super hydrophobic. It is something that repels, and that has been put to many use, and that can be mentioned, including in the rear view mirror in the cars, etc., so that when it rains, water doesn't stick to it for the physical. Of course, we can make exactly the opposite, super hydrophilic, where the water, you can see as soon as I put, just spreads completely and makes a thin film on top, because I have made it exactly opposite structure of this one. Then I can take these nanomaterials and arrange them. This is a beautiful opal, a semi-precious gemstone. It has these beautiful colors. These colors are actually colors not coming from the material, but it's diffracting light and light interference is giving rise to color, and that is known in the insect world also. This wing of this beetle has this beautiful color is not because it's green in color or emitting green light, but it is causing an interference of the light falling on it, giving the green and intensity that we can perceive. And we can arrange material today artificially in any kind of structure that you want. And we can arrange them in such a way that even it will become completely invisible so that the light will not penetrate to go around it like this, such that you can make invisible materials. These are called metamaterials, where the material is arranged in such a way to interfere with the wave property of the visible light, to manipulate visible light in a way so that it can become invisible. Not only visible light, you can make it invisible to radar also at the radar wave. What I'm showing you over here is a truly a nanomaterial, a transmission electron microscope picture of it. And there are these dots that you're seeing. These dots are actually columns of material, columns of atom with gaps between them, the next column. So this is a plane of atoms that you're seeing here. Beautiful. So we are able to make such materials. We are able to arrange such materials. But why should I want to make such materials? What is the advantage? In macroscopic world, if I take a large red ball, break it into smaller red ball, it just remains a red ball. I mean, if you think of it gold, it doesn't matter how much smaller I make it, it is always a gold particle. It looks like a gold. But if I break it down such that it's now in nanometric size, then a gold will begin to change its color, so that its physical and chemical and every property begins to change when I change the size. So having control on the size gives me this tremendous power out of the same material, getting all different kind of properties. This is of course just an illustration. Let me show you a real life example here. And this is the example that I think Professor Samir Sapra of IIT Delhi had created many, many years ago. Here what he had put is cadmium selenide, one particular material, cadmium selenide, just so. But of different particle size. The cadmium selenide particles here are larger in size, and here progressively making it smaller and smaller, and it's the smallest size. And what I'm going to do is to look at the color they give out when I shine UV light, because they're fluorescent materials. So they'll give us some kind of, they're luminescent materials. When I shine light on it, this is in the normal visible light. I'm going to shine UV light on this one, and you can see it gives beautiful blue light. Cadmium selenide. The same cadmium selenide as different size gives me green, another shade of green, yellow, and red. So I can get the same material to give me any color that I want out of one single material just by controlling its size. And the reason this happens is, of course, as you know that this material, the way luminescence happens, let me tell you just one short discussion of why, though I said that I'll not talk about the why, but here I'll tell you, it's a semiconducting material. So we basically have valence bands here, which is filled with electrons, and these are the conduction bands, which are completely empty. So there's this band gap, which characterizes semiconductor or an insulator. So it's not a metal. These are where the electrons are. This is where there are no electrons, but electron can go there. What I'm going to do is to take one electron from here and put it up there. How can I do that? I have to give energy, right? I mean, this electron has to go up in energy because energy increases that way. So I provide it energy by providing it some photon, high energy photon. So now I have a hole here where the electron was, and there's an electron there. But this electron can come down very quickly, and this hole can go up very quickly by using these other states. Once they come to this state, this electron cannot trickle down anymore. This hole cannot trickle up anymore. So the only way they can combine is by jumping down. When they jump down, they have to give out, the energy conservation requires that they give out a photon, a light, such that that light will carry the band gap energy. And that is exactly what happens. And that is the luminescent color that I see. And if I'm able to change the luminescent color, that means I'm being able to change the band gap. So I can tune the band gap by changing the size. So if this was the band gap, I'm either, this is the valence band with a hole there and an electron there, and if I want to change it, I have to either push the conduction band up or push the valence band down or do both simultaneously. And this is exactly what we do by changing the size. How do I know? I can test it. I can do the experiment. How can I measure the band? Measuring the band gap is very easy. I'll do the reverse process. What I'll do, I'll come with photons which have energy that are small, only this much. That means this photon cannot take an electron from here and put it there. So this photon cannot be absorbed because you see that is the smallest energy I need to make an electron excited. Because electrons are here, no electron there. To take an electron from here to there, I need this much energy. This photon has less energy. So I increase the photon energy a little, it still cannot carry. As soon as my photon energy becomes equal to that, I'll create an electron going up there. That means that photon will get absorbed. So I'm going to bring in photon and continuously increase the energy of that photon and see where the photon begins to get absorbed. Otherwise, the photon will get transmitted. This is the experiment that we do. This flat part is where the photon is getting transmitted. In this direction, I'm plotting absorption of photon, and this direction, photon energy. You can see for this material, it didn't get absorbed till photon energy was very high, and then it started absorbing. That means it has a band gap that is this much. Whereas this material, this first red one, started absorbing right here. So it has a band gap here, which means that the band gap is changing from here to here. And let me tell you that all this material is one material, zinc oxide. And I am only changing the size of the zinc oxide nanomaterial and tuning the band gap contents. So we can change the color, we can change all properties and make such beautiful colors by choosing the right material. And of course, colors can combine. And when different colors combine, I can make white light, and that is the kind of white light that can be generated. And these are the kind of white lights that are going to illuminate your house because these consume very low energy and can give very high efficiency light. And in fact, this kind of semiconductor nanomaterials are being used for high definition color TVs already. Many of the color TVs today come with these nanomaterials for the light emissive purposes. And of course, lighting application of this kind. How well can I organize? I said that I can make them, but can I place these small materials? They're so small. I cannot hold them with my finger. I cannot hold them with a pencil. How can I manipulate? We can manipulate them. I'll only show you examples. The extreme example of how well we can manipulate. And this is here where you can see that these little dots, this is the side view, this is looking from top. Each of these dot is actually an iron atom. And that this surface is a copper surface. And you have arranged in a particular way iron atom next to each other like this, giving rise to what is called a quantum quarrels, because it changes the properties of this copper surface. You can see the copper surface here looks mono, and here there is again pure copper, but looks totally different because I have modified the copper surface by putting this confinement of irons all around. But the main thing that I'm trying to point out to you is that I can how manipulate down to the atom level. I can place an atom where I want. Atom and molecule. For example, this doll that we see is actually carbon dioxide molecules placed next to each other in a systematic way, making this carbon dioxide man. Here, again, iron has been arranged on copper, and kanji characters, Chinese, Japanese characters, it says atom. Here, xenon atoms, these are each is a xenon atom arranged on nickel. This was created by a company. I cannot disclose the name of the company because it's a top secret. Of course, that's a joke. If you pay attention, you'll see the name of the company is exactly what they have written using xenon. So they can place atoms where they want exactly as they want. But why do I want to control at such small length scales? What is the purpose? What do I gain? The kind of gain is what has led to the revolution that you hold your mobile today, which has so much of power. All of them have processors. Look at the processor, how they're all processors, the computer chips have basic element as transistor. Each transistor takes some space. The question is, what is the size of that transistor? In 1971, the smallest transistor that you could make was 10 micron in size. And on a processor chip of more or less the same size all through the years, we could put 2,300 transistors. As we kept making the transistor size smaller, starting from 10 micron down to 180 nanometers, the same size processor, now starting from 2,300, now can have 42 million transistors. And that's the reason why the power of competition has gone up so much. But that was in 2000. Since 2000, you see that the feature size, it has gone from 180 nanometers in 2016, 22 nanometers. In fact, today, that's the reason the number of transistors per chip have gone up enormous, as I was showing you before. And today, the chip size, the transistor size, has gone to sub 10 nanometer technology. So that much smaller size gives you so much more power. And that's why this revolution that has come, which is so familiar. In fact, when I was young, in my student days, IBM 360 was one of the most powerful computers. And this computer, you can see how big it is. This is the two men standing here. The computer took the whole room. Let me tell you about its power. That had 20 megaflop of calculation power. My laptop today has 7,000 megaflop of calculation power. And the size of my laptop is, of course, extremely small. This larger 360 models had 8 megabytes of RAM. How much memory it had? My laptop has 16 gigabytes. That has a main storage of 1 megabyte. My computer has more than a terabyte of memory. So you see, the miniaturization or ability to control at small size has given the revolution that we have got so much used to. In fact, to show you the increase in the computing power 250 times from there, in the memory 2000 times, and in the storage device it's 1000 billion times. Here is actually a picture of one of the early storage devices. This storage device could store 5 MB of data, and that needed for transporting a crane and had to have a specially chartered plane to fly it from the IBM's to wherever it had to be delivered. And that is only 5 MB. As I said, today your mobile has many more MB, in fact, gigabytes of storage there. And the way this can be done, and I'll be skipping a few things now because I've taken a little more time than I wanted to. We can make transistors using one electron, controlling just the behavior of one electron. And this is what is shown over here. This is a device, there's an aluminum, this is the gauge where I'll be applying voltage and ionize this tellurium ion atom that I've implanted in silicon, making this electron move towards this, and by that allow this aluminum to that aluminum conduction to happen whenever the atomic level of this tellurium matches with the Fermi energy. And and that is shown. Okay. This is again a video. Basically, it moves up and down, and then it flows through. Current can be controlled by moving these levels up and down by applying a voltage here. Just controlling one electron. Similarly, we can now changing to different kinds of examples in the nanomaterials, molecules. This molecule looks like a car. If I think of these as wheels, because they can actually rotate around the axis. And this is the body of the car. And given the right kind of stimulus, they can rotate. And we can make them rotate all in the same direction, then the molecule will move like this. And let me actually show you an example of that. You can see that in this case, I've put these molecules in a way they are all rotating in the same direction so that there will be a linear motion. And you can see that here, This is the molecule and I'm tracking it and it's moving systematically, starting from here, ending up somewhere there. It started from here, ended up. In this particular example, I've put the two wheels against each other. This tries to move it this way, this tries to move it this way. So then this cannot move at all. And this is what you'll see now happening, that this will try to move but cannot move away from its place because the wheels are misaligned. If I now put the wheels in a way, sorry, if I put the wheels in a way that this set will move this way, that set will move that way, then it should be rotating. And that is what I'll be showing here. This one is rotating continuously. Yeah. And in fact, I can track its trajectory and it will be moving like this most of the time because of the way we put the wheels on this molecule. Now, for the last 2-3 minutes, I'll just quickly talk about this wonder material of today, which is the one that I would have talked about if I were to give a proper scientific. But this is something that is causing enormous amount of excitement in the energy sector, and that being a major theme of this particular meeting today, I will be talking about a little touch on it. This is a completely new generation of optically active materials, and it's being looked at among many other spectacular uses, a photovoltaic material. And I've shown, and it's competing with, not quite competing with, but supplementing the silicon technology that we have today. And we've been working on it, it's supported by many, but since I'll not be showing you any result from our particular work, I'm not going to spend time. What I'm showing you over here is actually, this direction is the year. And in this direction, the solar cell efficiency. Of course, we want the efficiency to go. And there are different colors and symbols you can see here. Each color and symbol is actually tracking the technology, how the efficiency is increasing. So you see, as time goes by, slowly the efficiency climbs up. Okay, for every technology, efficiency climbs. So let us not look at all different technologies. Let us look at the technology that is commercially available, the silicon technology, and that is given by the silicon technology, polycrystalline silicon, is this open blue squares. And you can see how slowly it is increasing. This is the single crystal silicon technology. Since it's crowded, let me surround the technology's growth by this ellipse. And this major axis of the ellipse is actually tracking how the efficiency on an average has gone up. You can see starting from 1975 or so, starting with an efficiency slightly over 10%. Now we have reached in the order of about 24% in this particular case. And you can see we are sitting here about 26, 27% we have reached with the single crystal, and here is the polycrystal, which is sitting close to 24%. Oops. Right? Now, I'm going to show you another material, this wonder material, which is here. It is discovered, its properties are discovered essentially around 2010, but in the last few years, it's gone up very quickly, and you can see I've expanded it here. And in this slide, I'm comparing it with the silicon technology. Silicon technology took 40 odd years to come to increase the efficiency, which this particular material has achieved in less than 10 years and has come to the efficiency that is equal to the silicon technology. So it's really spectacular growth of this material that has given rise to this. Only efficiency is good. Actually, it's much more than efficiency. You know, all the time we want to make the silicons, the solar cells thinner and thinner so that the weight is less, so that it can mount it everywhere. But in order to make it thin, it must absorb very efficiently. And that gave rise to new technologies called Dyesensitized solar cell, that with 10 micron thick layer, active layer, you can do the solar cell. Then we went to solid state Dyesensitized solar cell that was about half a micron or 1 micron thick. Extremely thin solar cells, based on similar technology with improvement, came to about half a micron. Whereas this new material, its absorption power is so strong that it can make the solar cell less than half a micron thick. Not only that, this dye-sensitized solar cell that I talked about, there the material, that photoactive material which absorbs the photon, is normally a thin layer. But the electron and hole that we generate is conducted by, on one side, electron is conducted by titanium dioxide, on the other side, you put another hole transporting material so that they get separated, because in general, the material is not good for, it's not good mobility. So you need, but it turned out that this material did not make titanium dioxide, and this was proven by replacing titanium dioxide with aluminum oxide, which does not conduct electrons at all. And it was found that the efficiency didn't go down at all. So that got rid of these things altogether, and it turns out that this is not only absorbs very well, but it also has high mobility for electrons and holes. What makes it so good? As we know, what we need to make a good solar cell material is that it must have good absorption of light. It must give rise to slow recombination of the electron and hole that is generated, because if it recombines very quickly, then of course you won't get electricity outside, it gets recombined inside. And it must give rise to high voltage also, because the power that it generates is voltage multiplied by the current. And on all those counts, this particular material or this family of materials, which are known as hybrid perovskites, because it has an organic part, CH3NH3, methyl ammonium, and an inorganic part, lead halide, put in the perovskite structure. And so this material has been known again, but nobody knew how fantastic it is. It has almost ideal band gap, a little less than 1.6 fold. It has an absorption coefficient which is extremely high. It has very long carrier diffusion length, and it is very high open circuit voltage, giving rise to very high power. But is that all? I'll end with this question, because it turns out that it's not all. This has such fantastic, exciting properties due to the presence of this organic molecule that can rotate, that can freeze, and that couples to the behavior of this inorganic cage, and in coupled manner they behave in a way that is so surprising that we're discovering newer properties each day, which makes it interesting beyond also the solar cell application. With that, telling you a whole series of different exciting materials, their properties, why they're exciting, and the excitement to understand why such properties exist, where we spend all our time. Let me hope I have been able to share some of that excitement with you and end my talk thanking you for your attention. Thank you very much.
Thank you, sir, for very informative and wonderful lecture, sir. And most of the participants are giving their comments for and giving you thanks for your lecture. Actually, I know, sir, you have to rush to your meeting, but some of young scientists have raised some questions, sir, if you allow, sir. Yeah. Sir, one participant has asked one question: which metals are used to make a shape memory alloys?
These are very complex alloys made of many materials, manganese, nickel. Some of the transition elements are there, but many others. In fact, if you want, just give a Google search and it will tell you all the compositions immediately. These are multi-component alloy systems.
Yes, sir. Sir, are there any organic superconductors?
Oh, there are. There are organic superconductors, several of them, which are again a very surprising thing, because we didn't expect organic materials to be superconducting, particularly because metals, and we associate superconductivity normally with metals, and metals we associate with broad band, but organic materials have very narrow band, and yet they can show superconductivity. And that's again a totally fascinating field of study.
Yeah. So we are getting more compliments rather than the questions from your lecture. One more question from sir, our undergraduate student. How far can TMD materials go if 1 volt potential is applied?
What? Sorry, I didn't get it.
How far can TMD
Okay,
material go
transition to
to
dialpha. Yeah. So basically, the mobility again from MOS2 etc. can be made very, very high. It's not as good as graphene. I don't remember the number, but they're spectacular. But also, I must point out that much of mobility improvement is technology driven in the sense technology driven and science driven. Zinc oxide, which is a three-dimensional material, not two-dimensional. If you make it extremely pure, it has been shown by a very close friend of mine, Kawasaki, you can have a 1 million mobility. So it's extraordinary. So basically the mobility, see, the point is like Newton's laws of motion. If you make an electron start to move, unless it collides with something and dissipates its energy, it will move. So it is the mobility is restricted by the scattering processes. And much of it, there's of course intrinsic scattering processes associated with temperature because all atoms are vibrating in a solid, but the dominant part comes from defects and impurities. And that's why silicon needs to be made very clean and pure in order to achieve very high mobility to make it suitable for the silicon technology. TMDs are also very good materials and can have very high. But I wanted to give the complete answer that you can make other materials also. If you can make them very pure without any defects, you can achieve high mobility.
Again, it's a very general question, sir. What are the harmful effects of nanomaterials in near future?
In near future, let's say what are the harmful effects of nanomaterials? Any material has harmful effect, right? Copper. I mean, whoever has asked the question, I want that person to think for a moment. Copper, can it have harmful effect? If you say no, then you say that you didn't grow up the way I grew up. Once I took copper cable and put it when I was very young and put it inside the plug point and got a huge shock. And that was so copper can be harmful. You can electrocute me using copper. So it's a question of how you use it. Okay, but I didn't want to trivialize the matter. There is an issue that you have to know about nanomaterials. Nanomaterial size is typically so small that they can go through the biological barriers easily. This is the issue that people talk about, the danger of nanomaterial, because it can go across the biological barriers. Typically, when you get below 25 micron, it's too small and it can go through the pores of biological systems or biological protections and can be ingested by biological systems. And so one has to worry about it. And it's a very specialized topic of many experts studying it. I am not an expert. So there can be adverse effect and so we have to be careful. But it's a question of knowing, understanding the risk and taking care of it. So I was trying to point out everything has some risk, but we need to understand what are the risks and how the risk comes about and how to mitigate that risk. And that is how every technology has flourished.
One more last question, sir. Actually, I know you have to go. Very simple question, sir. We can have materials which can actually switch its properties from hydrophilic to hydrophobic properties into each other. Can we have that kind of materials in which the hydrophilic properties can be switched over to hydrophobic?
It is thinkable. I mean, I often cannot think of examples, but I would not be surprised if such a paper exists, such work exists. Simply because what you have to do, remember, the way it has to be done. I mean, if I am given this task, how will I think about it? The way I'll think about it is, of course, what I'm doing is to put some functional materials on top of a material, and that functional material end has the property of repelling water, doesn't like water. Let's say coating something with oil, essentially that. Now I need a material. So, but then I want to change its property. That means I need a phase transition material, which at one stage in one configuration has a hydrophobic end and another configuration has a hydrophilic end, and I should be able to switch which end is pointing outward by giving light or temperature or some such thing so that I can flip it back and forth, making it hydrophilic or hydrophobic. So it is thinkable to achieve, but I do not know if it has been achieved or active.
So can we apply materials to capture water from atmosphere?
Oh, there is a lot of work going on in many different ways. In fact, I mean, this is all inspired by these beetles in the desert that go up on the top of the sand dune and put up their legs, and their legs have very fine structure, almost nanostructures, which are now the air passing through them, the moisture condenses on those legs, and then they get their drops coming down, and that's how they get their source of water. And in fact, there are ideas of trying to get that technology to work in areas which doesn't have enough water, potable water. That's one of the technologies, but it's, I would say, commercially not yet viable, but prototypes exist, and those kind of technologies have been set up and shown to work. Yes.
In such beautiful way, you are actually explaining the giving the response of the queries of the undergraduate and postgraduate students. So more queries are coming.
We have some more time, a few more minutes if you want.
So if you have 1 or 2 minutes, we can take
Sure,
one or two.
please. Please.
Yeah. So can carbon nanotubes technology or nano carbon tube technology could be used to make lightweight spaceships to cover large distances in space?
I mean, surely the point is that actually these carbon materials are in various forms in composite and in composite forms primarily, are being used for lightweight applications because they provide additional strength and at the same time make the material much lighter weight. So definitely it will be used, and also it needs to be heat resistant. So it has to be some kind of composite material with which I don't know whether in rockets it is being used. But since in rocket technology, like in any aviation technology, other aviation technologies also, the weight is an extremely important criteria. I'm sure that it's being and being used for all I know.
Yeah. The last question, sir. Yeah. Is potency and stability of composite materials is less than pure materials?
Pardon?
Potency and stability.
Potency and stability.
Potential and stability of composite materials is less than pure materials. How would we compare the stability of composite materials and the pure materials? Like for example, sir, we have the steel, we have the composite, and if you have the pure carbon or pure iron, like brass, pure we compare with copper or zinc, something like that, sir.
Okay, so see that in general, I mean, first of all, one would not make a composite material if some property did not improve. Because the idea of making composite material from pure material is to improve the material strength. In general, composite material has enhancement of various kind of crack resistance, and simply because what happens is that you make in a composite material, it becomes very anisotropic. So crack propagation and other things gets blocked. Okay, so that's the reason composite material in terms of mechanical properties have been used from even before they understood the science behind it. Okay, but there are many properties where a composite material is not a good idea. For example, if you want to conduct electrons, now, if you have a composite material, precisely because the crack cannot propagate, also for similar reason, the electron cannot propagate. Electron wants a very beautifully periodic system to be able to propagate. As I said, that even a defect in that pure material causes some distress to the electron. An electron is not able to move as well as it can. So electron movement would require very nice property. But that metal, if it doesn't have the mechanical strength, and you want to give it a mechanical strength, then you give to something to it to provide it the material strength by making a composite, but where a large part of the metal is the one that will be carrying the electricity. So it's difficult to discuss this particular question without specific examples of which property we are talking about and what kind of material. Then one can give a more clear answer to this.
Actually, sir, we are receiving some more questions, but I would like to tell the participants, actually, those questions are more specific to the talk of Professor Ashok Kumar Ganguly and Professor Chari on water purification and the environmental issues. So we will ask those questions in those sessions, sir. So, sir, I would like to, sir, thank you so much, and we are getting more compliments from the audience side, sir. And the Madam Vice Chancellor was much happy, sir, to see you again here in Jamia. She was very pleased to have you, sir, in this program. And in fact, she was actually attend your lecture nearly half an hour. Then she went for
Wonderful.
meeting. Yeah.
My compliments, convey my compliments and congratulations to her to have put together such a fantastic team and for supporting you people for doing all this. And compliment to you, Professor Ahmed, and your entire team and your colleagues, your dean, registrar, everybody, and the participants for putting together such a wonderful. It's been my pleasure, and hopefully things will become better and we'll meet in person.
Thank you so much, sir.
Thank you so much.
We will meet again. Have a nice day, sir.